This is ECE 343 Segments and Systems. This will be the fifth part of Chapter 4. In today's lecture, we're going to focus on system realizations. So we're looking at the case of having constant coefficient linear differential equations, and we'd like to think of structures that will allow us to realize these systems. In order for us to do that, we're going to focus on a second order system. The reason I do that is because a second order system is the lowest order that can realize successfully systems, general systems, while using real coefficients. If you have a system that happens to have a complex pole, for example, or a complex root, if the system was real, it must also have the conjugate root. That's just a necessary condition for these differential equations. If you look at the polynomial operator Q or P, if those expanded polynomials have real coefficients, while the roots might be complex, the coefficients being real forces any complex roots to come in conjugate pairs. So we would grab those two conjugate pairs together, multiply them out, and that would give us real coefficients. So we're going to stick with a small order, the lowest order that is possible to realize a general system, right, that still maintains the ability to deal with complex roots. Any of these structures that I look at in this lecture can easily be extended to higher order systems as a direct realization. So let's go ahead and start. We're going to go ahead and concentrate then. Let's going to concentrate our efforts right now. We're going to concentrate on realizing a second order system. And it's easily extended, as I said before. So let's go ahead and write out the constant coefficient linear differential equation for a second order system. We have something like the following. We can take an a0d squared plus an a1d plus some a2, right, acting on y of t, being equal to some b0d squared plus b1d plus some b2 acting on x of t. This is the standard form constant coefficient linear differential equation version of this system, second order system. And one of the problems that we have with this particular one, at least from a realization standpoint, is that derivatives in themselves tend to amplify noise. So if you think about a differentiation operation, we know differentials are a slope, right? They're a rate of change. And so that might work very well. But if you have a signal, right, you have some sort of signal, and there it is, you've got some sort of signal going in there, you can differentiate that, and for kind of low frequency signals, that's no problem. But we know in real life there's extra little bits of noise on there, right? So maybe you get a little bit of noise added in on that signal, and if you do a DDT type of operation on that, right, the underlying sinusoid there is just going to give you another sinusoid, so you're going to get that kind of problem. But those little tiny noise pieces, which have some high frequency components, they're rapid changes. A DDT on that guy can cause this amplification of noise, something along those lines. So it turns out that while we oftentimes represent systems using a differential form, that differential form is probably not the way we want to realize them, because derivatives tend to amplify noise in the presence of that non-ideal condition of having noise on our signal paths. So instead, we would prefer to have an integral form. So I'm just going to make the comment here that DDT is an operation. DDT tends to amplify noise, while the idea of an integral tends to suppress noise. So when you integrate the little tiny oscillations that might be the noise on there, it tends to smooth it out. And so we are going to prefer an integral form. As I go with this then, I'm just going to note we thus prefer an integral form for realization. Also, we usually, and I can't think of a case when we wouldn't, normalize that lead coefficient for the highest order power of derivative. So we normalize the a0 coefficient equal to 1. If it wasn't equal to 1, you just divide the entire equation by 1. So if we look back at this guy, we have a second order differential equation. I'm going to go ahead and grab this guy, copy it down, and then we're going to convert it to an integral equation. So this is differential equation form, and we'll just make this into an integral form, recognizing that that integral form is really the one that is going to provide us the best noise performance of our system. So if I take this guy and I just double integrate it, in this case it's a second order system, so if I double integrate this guy, I can get rid of all of the derivatives. And then I also note in here a0 equaling to 1. If I do that, the double integral of a derivative squared, right, is just going to be the signal by itself, and a0 was 1, so I'm going to get a 1, and I'm going to have a plus a1. Double integral of a first derivative is just going to be an integral, right? And then I'm going to have double integral a2, all of these guys acting on y of t, right, being equal to, I'm going to have b0 plus b1 integral plus b2 double integral acting on x of t, something along those lines. So this is an integral form of the same system. Both of these two, right? If I look at this first expression, the derivative form, and the second expression, the integral form, they both describe exactly the same system, and it would be identically the same if it was a perfect condition like a no noise condition. However, in the presence of real world noise, we would tend to prefer that second realization, that second representation, because it involves integrals which tend to suppress noise rather than differentials which tend to amplify it. Okay, so what do we want to do? We want to be able to realize this system. I'm going to just write it in a little bit different form. I'm going to go ahead and solve for the yt term in this case. So that's going to come from this one here, the 1 times y of t, put that on the left-hand side and put everything else on the right-hand side. So I'm going to get a y of t being equal to, I'm going to leave the input terms first, so I'm going to have a b0 x of t, and I'm going to have a b1 integral x of t, and I'm going to have a b2 double integral x of t, and then I had on the left-hand side an a1 integral y, which I'm bringing to the other side, so I'm going to have a minus a1 integral y of t, and there was that double integral a2y of t, which I can write out as a minus a2 double integral y of t. Okay, so this is the equation I want to realize. I'm going to have a structure that can output this desired output, y of t. It's going to involve some dependence on the input. So there's an x and its integrals, right? So we've got a couple of extra terms in there. And it also depends on feeding back that output term through some integrators as well. So there's going to be 5 full terms coming into this to create my y of t term. In order to do this, I'm going to notice that there's a few things that I need to be able to do, right? I need to be able to multiply numbers together, right? So I'm going to have some sort of scale factor and then the multiply. Those are things I'm going to need. I'm also going to need some sort of integration kind of ability, and I'm going to have something that's going to allow me to sum. If I can have those 3 basic operations, so I have a multiply by a scale factor, a summation, and an integral. If I can get those 3 pieces in there, I should be able to realize this equation. Let me go ahead and start by just drawing out the structure directly from this expression. I do know that I have an input x of t by convention. We go ahead and write that input on the left-hand side on here, and that input is gonna start going forward, right? So we've got this input in there. If I look at this, I see that y of t does involve x of t times some b0. So I'm gonna go ahead and put a gain factor in here. I'm gonna have a little amplifier with some gain b0. And what comes out of that term, right, is b0x of t. That's one of the terms I need. Because I know where I'm going to go ahead and show some additional summing nodes in here. This is just going to be because I do recognize where it is that I need to go. So I'm going to go ahead and leave enough of the structure in here so that I can make some efficiencies in the end diagram here, and so we can get a little bit of additional insight. So we're going to go ahead and have that keep going forward. I'm going to go through another summing node. We'll see why we need these summing nodes here in a minute. And eventually, right, we're going to come out of here and get our y of t. So as drawn right now, even though those summing nodes don't have much getting summed into it, I see y of t equals b0 x of t. I'm going to go ahead and highlight the terms in this expression that I've taken care of. So I just took care of the b0 x of t as part of this. One of the other terms that I need is I need the integral of x of t multiplied by b1 to be added in there as well. So what I'm going to do in this particular case is I'm going to go ahead and grab my x of t, right? and I'm going to run it through an integrator. So I'm going to go ahead and draw a block here. I'm not too worried. We'll later look at some circuits that allow us to carry out each one of these operations, but for right now, we're just going to assume I have an integrator block, a summing block, and a scaling block. So I'm going to have a little integrator block here, and what comes out of here, right, it's just going to be the integral of x of t, and I know that that guy needs to get multiplied by some b1 gain, and that's going to get summed in here as well. I'm going to show another summing node here just because I know where I'm going and I want this thing to look nice and clean and neat before everything is done. So at this point, what have I done? We can see two feed forward paths. I call them feed forward paths because the directionality of the arrows is all going forward towards the output term y of t. We can see right now that y of t equals b0x plus b1 integral x. So we just added in that second term. This is all being done directly from writing out the expression for y of t based on our original differential equation once it was converted to the integral form. There's one more term that depends on x, right? That's going to be this b2 double integral of x. And so I'm going to need to have the double or second integral of x. I've already got the first integral of x, so why not utilize that? All I need to do is run that particular one through another integrator, right? And so if I took the integral of x and I integrate it again, I'm going to get the double integral of x. That's probably more efficient than having a separate path that has to get integrated twice, right? That would be getting charged more than we need to in order to carry out that operation. So we use what we've had before, and then this guy has to get multiplied by some, what was it, b2. And that's going to come in here and get summed in as well. So I end up having, in this case now, that third term that involves the input, right? So I've just taken care of this guy right here. I have b2 double integral of x. What I have now left to take care of is I got to feed back some of these terms related to the output. I see that I need a minus a1 times the integral of y. So I'm going to know that I've got y right here, right? And so if I can run this guy also through an integrator, right? I would have at this point integral of y of t, right? And I think you know where we're going on this. I'm also going to need, because of the very last term in there, another one that is the double integral of y of t. So let's go ahead and get that started in there. So the first one in there is minus a1 times integral y needing to be summed in. So I'm going to feed this guy back, right? And it's going to have its own amplifier, but it's going to have a minus a1 on there rather than a plus. We get a negation because all those output terms got taken to the other side of the expression, to the other side of the equation. Going to run into a summing node in here, and that guy's going to feed in, and it's going to feed back up to give me back my y. At this point, what do I have? I have all the feed forward terms involving all the inputs. So I have b0x plus b1 integral x plus b2 double integral x. And because of this second loop in here, right, this loop right here, that particular loop right there says, give me integral y multiplied by minus a1 and add it in as part of my expression for y. So that is, in this particular case, this next to last term, minus a1 integral y. The only one left is minus a2 double integral y. I've already drawn out, getting out double integral y. I just need to multiply it by the appropriate scale factor in this case. So in this particular case, I'm going to need a minus a2, and that guy is going to get summed in as well. Now I've got a complete structure, right? I've got a complete structure that is a realization of that second order constant coefficient linear integral equation that was reflective of a general second order system. Some things to notice about this guy. It has, right, input on the left, output on the right, and then we've got a bunch of stuff in between. So that's our system, right? We can see that it relies directly on the coefficients from my original differential equation. If we take a look at those guys, if I look at this first part in here, right, this has got all those b coefficients, right? So this is the part that realizes, it realizes the PD part, the PD or system zeros, the system zeros, the zeros of the system, right? The system zeros. We know that that PD is the system zeros. We'll come back. Well, we can do that right now. The transfer function of an LTI system, H of S, is what? We could get it as output over input, Y of S over X of S. We can also get it from those coefficients that were from our original differential equation. We had, what was it? It was P of S over Q of S. And remember, P is just that polynomial operator acting on the input variables. That has all the B0, B1, B2 type of coefficients, right? any root to that polynomial p, right, gives us a value of s that would cause h of s to be equal to 0. We'll come back to that. The system zeros, right, are values of s for which h of s evaluates to 0. The second part of this guy right here, this guy is all about, this realizes stuff, realizes the QD part, or the system poles, right? It's all of those coefficients, A1, A2, all the way out to however high order system it is. It's all that stuff that makes up the Q. And I know that the Q, if I look back at my expression for h of s, Q of s is the thing in the denominator. So if you found a root, a value of s that is a root of that denominator, you would get 0 in the denominator, and that would make everything blow up to infinity. So a very quick little aside, I'm just going to do this as a recall, right? Recall that if we take an e to the st, an everlasting exponential, into our system, right, and we look at what comes out, we get that same exact everlasting exponential times h of s, right? So everlasting exponential in gives us everlasting exponential out, right? If s is a system zero, if we choose our input frequency, right, that matches with the system zero. What is a system zero? It's when h of s equals 0, and that really implied that b of s was equal to 0. That's the numerator of h of s, or I guess I couldn't have called that b. I'll call that guy p. It's also called a and b in some contexts as well. So let's just go ahead and leave it as what I said before. So we have our p of s. I guess I could make that a red one as well. So that's going to be our p of s from our original differential equation. So that's when p of s equals 0. Okay, that is the idea of a system zero. In that case, if s is a system zero, right, then what happens? E to the st goes through the system, right, and it becomes e to the st times 0, which equals 0. Okay, so if you are at a frequency near a system 0, the output gets small. Okay, that's an important conclusion for us. So let's go ahead and mark that down. If the input, right, is near or at, right, a system 0 in terms of frequency, right, near or at a system 0, right, the output is small or 0, which is part of the reason they call it a system 0. It zeroes out the input, so to speak. Now, if we go to the other extreme and we take an input that has a frequency that's near a system pole, so if I do if S is a system pole, right? And what did we call a system pole? That's when h of s goes off to infinity, which really required that q of s being equal to 0, right? So finding one of the roots of the denominator, then what happens? Then e to the st goes to e to the st times infinity, right, which goes off to infinity. We get this extremely strong kind of output, right? If you drive a system at that pole, right, you end up getting an unbounded output. So we can get a conclusion out of this as well. If an input is near or at, right, a system pole, you can think of a pole as something that pushes stuff up, makes it larger. It's near a system pole, right? The output then, right, the output is large and maybe even tending off to infinity. So let's go back to our structure. We have a structure here that realizes the system zeros first, and then it realizes the system poles. So in this particular structure, we have the zeros first, followed by the poles. The input comes in, it's made smaller because of the zeros, right? That's this first part right here. This thing here tends to make things smaller because that implements the system zeros. And then those poles pull up the response to the final desired value. So that's going to make it larger. This particular ordering of zeros first followed by poles is something that is desirable. It is less likely to cause overflow of components. If you had the reverse order where you did something that had the poles first, you could make things very large, and then the system zeros would want to make them smaller. But in the interim, when you made it really, really large, you might have caused some overflow with one of your components. So I'm going to put a little metric for kind of how we like this structure. And I'm going to note in here that there are the zeros, right? then leading to the poles, right? And that ordering, I'm going to give a real happy face, okay? So that particular thing is a good element of this structure. Zeros first followed by poles tends to reduce the overflow potential of this realization. There's another thing I want to look at just briefly when we think about this structure as a way of implementing the system. Implementations, realizations are not unique. We're going to look at a total of 4 different realizations today, at least. And so these 4 different realizations are all going to have different kind of characteristics, okay? And one of the things I'm also going to note in here is that there's an integral, right? An integral, and an integral. So there's a 4 number of integrals. So the number of integrators, which in this case equals 4, I'm going to say does not equal, it's greater than, right? The number of, or the order of the system. So maybe I'll just write this out as the order of the system. I have a second order system, but I'm using 4 integrators. That in a sense is going to turn out to be not so great. We're going to look at later structures where the number of integrators, which is an expensive thing to build, right? If we look at the circuits to do that, we're going to typically realize an integrator with an op amp. So this guy's kind of like got 4 op amps the way it's drawn in here. If I could reduce the number of integrators that I use in my realization without changing the system behavior, right? Then it would be potentially a much better realization. This one has more integrators than the order of the system. This is called a non-canonical, so it is not the minimum order as far as number of integrators, so it's non-canonical, not the smallest number, non-canonical. And that is generally not a good thing because the number of integrators exceeds the order of the system. We'll find out later that we can do better. So this particular structure that I've drawn in here has some good things. The 0 pole ordering is good, but it has some not so great things. It has a kind of an overcharge or an excess number of integrators in there. It was also, in some respects, nice just because it directly followed from the differential equation or the integral equation that we had written as far as the system that we wanted to implement. Because it was written directly, okay, this thing led directly to that structure. They gave it a not so terribly creative name. They call this guy the direct form, and it's the first of the direct forms. It's called the direct form 1 realization. This gets to be kind of boring to write out every time, and so what you'll see it called a DF1. DF1 is just a realization of an integral system representation, an integral equation, right? And it's one that puts the zeros first followed by the poles. It's one that is non-canonical in the number of integrators, and it follows directly from the integral equation, something along those lines, a DF1. What I'm going to do here is I'm going to try to grab this entire thing so that we can kind of summarize everything that we had, because we're gonna play some games with this guy as well. So let me just go and make sure that I grab all of this guy, and we will clean it up a bit. So I'm going to go ahead and take this thing, and we're going to copy it, and we're going to move down and work with this guy a little bit. I will clean it up and hopefully be able to deal with it in a bit nicer way. So let's go ahead and get rid of everything in here other than just the actual structure itself, and I will label it at the bottom just a little bit. So this is DF1, right? We see that it was non-canonical, right? So number of integrators is greater than the order of the system. And I'm just going to put a sad face there because that's a less desirable characteristic. And then we also see in this particular case that it has zeros and then poles, right? So the ordering of the poles and zeros is one that helps reduce the likelihood of signal overflow. And so I will call that a good characteristic of this overall structure, right? So if I look at this overall structure, DF1, it has good characteristics and not so great characteristics. Okay, so first of 4 structures that we want to look at, comprised of integrators, multipliers, and sums. Here's what I would like to do in trying to work towards something else. I'm going to get another direct structure, or another one that is called a direct form structure. And so let's go ahead and look at something that is going to be called direct form 2. So let's work on direct form 2 realization. And to do this particular realization, I'm just going to note something. So I'm going to say recall, right? Recall that if I have a signal x of t feeding into a system, I'm going to call it H1, that feeds into another system, H2, and gives me an output y of t, right? This is a realization of systems in series. I know that the overall system response, right, we could think of as H1 convolved with H2, or if I did this in the transform domain, it would be H1 of S, right, times H2 of S. Both convolution and multiplication, don't care what order you do the convolution or the multiplication in, right? So we know that this is the same as H2 convolved with H1, right? Same thing as saying this is equal to H2 times H1. And what that really means is that this whole structure here, right, can be equivalently done by taking x of t not into H1 first, but I could do it into H2 first, and then go into H1 and give us an output y of t. Those guys are equivalent, right? They are equivalent structures in this case, right? So we know that those two cases are equivalent. Let's go back and look at our direct form one. I've drawn this in a particular way so that as the order of the system got larger, right, these chains would just get bigger, right? If I had a third order system, I'd add another integrator, I'd have a coefficient B3, I'd add another integrator on the right-hand side, and I'd have a coefficient minus A3, and you could keep doing that to whatever order you wanted. I also can see in this particular case, and I'm going to just do this in kind of a different color. Let's go ahead and note that this first part here, right, is something that we could think of as an entire system, right? This was the zeros of the system. We'd already noted that before. And then we went in cascade to something that did the poles of the system. So if I go back down here, right, I can think of this as having my zeros followed by my poles, right? That was more along the lines of direct form one. Knowing the commutability of convolution or multiplication tells me that I can interchange the order there without affecting the overall system behavior. So I could do this poles followed by zeros, and that really is the idea behind direct form 2, this thing that we're working on, so DF2. So what I'm going to do is I'm going to recopy this entire structure, but I'm just going to interchange the order. So this is the advantage, I guess, of having these this iPad. Is that I should be able to go ahead and grab this whole thing, and then we will just do some cutting and pasting and make it a little bit quicker, so I don't have to redraw these structures out every time. So let me go ahead and paste this in. So we've got this guy, right? And we'll see what we can do in this particular case. I'm going to move this over just a little bit. I'm going to do a little bit of erasing, get rid of some stuff in here, and we're going to go to work on it. So what am I thinking about in this particular case? I'm going to go ahead and grab this first part of the system, right? That's this guy right here, and we know that we want this to get moved somewhere else. So I'm going to just set it off somewhere down here for right now. And then I have the second part of the system, right? And what I would like to do with that is I would like to move it first instead. So I'm going to come in here and grab this guy and move it in first, something like that. I will get rid of some of these labels because these labels are not going to be so important or accurate anymore. And I'm going to come back down here, and this was my second part of the structure, and I'm going to go ahead and grab it now and move it back up, right? We're just interchanging the order of these guys, something like that, right? Okay, so all I've done is interchange the two pieces. I haven't changed the overall system. I've just changed the order of the two things that were in cascade. So now what do I see here? Right now I see that I'm doing something that is the poles of the system followed by the zeros of the system. Now that we had already talked about, that might not be such a great thing. Poles tend to make something stronger, get bigger, and zeros tend to bring it back down. So if I do the poles first, I might make things large enough that things overflow before they get down to their final level with the zeros. So this is an order that can be more likely to facilitate overflow in the final implementation. So I'm going to give that a little bit of a frowny face. But what comes nice out of this particular one is the following. If you take a look at what I've got here, I'm going to go ahead and make a label in the middle here. I'm going to call this node here v of t. And notice that that's also this guy here, v of t. And so here we have integral v of t, and here we have double integral v of t. And it's the same across those two. So what I can tell on this particular case is that one of those sets of integrators, right, is really totally unnecessary. I don't need that integrator. I don't need that integrator. I can instead, right, I can instead just think about letting these paths go forward, right, and ignoring those integrators altogether. That's going to cut the number of integrators in the system realization down by a factor of 2 without changing system behavior. That is fantastic. So that is a nice kind of goal that we get out of here. So I can now say that on modification, right, on elimination, I could say elimination, right, of the redundant integrators, right, we see that the number of integrators equals the system order. That's a good thing, right? So that's a happy condition. That's going to reduce the complexity of the circuit realization. It's going to reduce the cost. It's going to make it a better implementation overall. So I'll clean this guy up and I'll write it out neatly. So I'm going to have my input x of t. It's just going to feed forward, right? Whoops, missed a summing node in there. It's going to feed forward until it hits a summing node. And then that guy is going to keep feeding forward until it eventually hits another summing node, something like that, out of which comes my output y of t. In this middle thing, I'm going to hit a chain of, I've got a couple mistakes in here. We'll be able to clean these guys up a little bit. Let's go ahead and fix these right now. This first one had a multiplier, B0. I do have to get those ones in there. I have an integrator in here, and then I'm going to go and get to another integrator, something like that. And then this guy here is going to feed back. This is going to be minus A1. And here I'm going to have minus A2. These things get summed up. So that's my realization, if you will, of the system poles. And then I have the ones going forward. I'm going to have a B1 here, and I'm going to have a B2 here. And just a reminder, take a look at how easy it is to draw these structures. If you have the original differential equation, you know these coefficients B's and A's, right? And you can immediately draw these guys down. So this one here is my direct form 2. This is my direct form 2. And what I can notice on this particular one, right, is that the number of integrators equals the order of the system. That's a very good characteristic. And I can see that this one does the poles, and then it does the zeros, and that tends to have a higher potential of overflow. And so that's a sad face. So if I was going to look at this as a realization, remember that these two different topologies, these two different structures, these two different ways of hooking up summers and integrators and op amps, these gain factors, right? All of these guys carry out, in this particular case, the same second order system, right? It's just that the realization is a little different, and in the practice, right, these different realizations have a little bit of a different chance of being having some characteristics that are good, like maybe with how it responds to noise, or the cost of implementing them, right? Fewer integrators on one of them. So this direct form 2 has basically completely altered the good and bad, the two characteristics we're looking at from direct form 1. Direct form 1 was a sad happy, and this direct form 2 is a happy sad, right? We just changed the characteristics on all of those. As you might guess, we would like to get something that is got happy happy. We would like a canonical, right? We'd like a canonical structure. This first condition here, right? The number of integrators being equal to the order of the system, right? They call this guy canonical. It is a canonical structure. Usually having a canonical structure, that means you're using the minimum number of components, right? The minimum number of integrators in this case for an nth order system. This is a canonical structure, but we would like it to have that good pole zero ordering as well. And so we're going to want to work towards that. I would make the comment in this particular case, this direct form 2 has another name that it sometimes goes by. So if you look in the book, DF2 is sometimes called this idea of being called a controller, what is called a controller canonical form. And it's a pretty common and a pretty popular way of realizing systems. Still, I'm hoping to get a happy realization. I'd like to have a canonical structure that also has its zeros first followed by its poles. In order for me to do that, I'm going to introduce a very simple transformation that can be done to any of these block realizations without altering their overall system behavior. So let's look at what are called transposed structures. Okay, transposed structures. Okay, if we apply the following steps, and I'm going to do this without proof, the following steps, okay, we obtain an equivalent realization, right? It's going to still realize that same second order differential equation, or whatever order you do. It's an equivalent realization called a transposed realization. It's the transposed version, right? A transposed realization. Okay, and the steps here are pretty easy. There's three basic steps. So the first thing we're going to do is we're going to reverse all arrows. Reverse all arrows. Okay, the second thing that we're going to do is that we're going to exchange. So just change places of both the input and the output. Okay, and then the third thing that we're going to do is a compound one. We are going to replace, all the summing nodes with just a joining node, and we are going to replace, if I can get this right now, we are going to replace all of the nodes, the joining nodes, with sums, something like that. If you do these three steps, you will not change the functionality. You won't change the underlying equation that a system generates, right? But you might change some of the characteristics. So let's go back and look at direct form 2. Direct form 2 right now has x on the left and y on the right. It does the poles first, followed by the zeros. That was a bad thing, but it was canonical. Think about what the transpose operation might do to this. Because everything is reversed, and because out becomes input and input becomes output, that would put the input on the right and the output on the left, which effectively changes the order of poles and zeros, something along those lines. So then we would get our zeros first, followed by the poles, and it would still remain canonical. That sounds like what we want. So I'm going to go ahead and copy this guy. We're going to apply the transpose operation, and then because I had done it without proof, we're going to verify that it indeed does the same equation that we had wanted before. So let's go ahead and put this in here. I'm going to go ahead and paste it in. And so here's my original structure. So this is the original that was my direct form 2, right? And I want to work towards a transposed version of this guy, right? What was step 1? Reverse all arrow directions. This is going to look like a mess to begin with. I'll clean it up in a second. So the biggest way I'm going to handle the arrow directions is I'm going to do mostly just from the gains. I think the other ones we can get here in a minute. So the gains, right? These all help indicate direction. So I'm going to reverse all the directions. Yeah, so we know that this is going to look a little messy coming in here. So that's that first step. All the arrows got exchanged in direction. The next one said what? Out becomes input, input becomes output, exchange the two. So output y becomes input x of t, and input x of t becomes output y of t, something along those lines. It also says that everything that was a summing node becomes just a regular joining node. So this guy here is going to become a joining node. This guy here is going to become a joining node. This guy here is going to become a joining node. And this guy here is going to become a joining node. And then the last part of that compound third step, right, was that anything that was a joining node is going to become a summing node. Well, here was a joining node, so it's going to become a sum. Here was a joining node, that's going to become a sum. Here was a joining node, that's going to become a sum. I've done all three of my steps, and if I clean this guy up, I should have what is called this transposed direct form 2. We still will want to kind of verify that it does indeed do the same equation. So let me go ahead and redraw this. Let's take what we've got here, but draw it in more the standard way and get it all cleaned up. Usually we have input right on the left, so I'm going to go ahead and just draw this guy kind of mirror imaged so that I can get the input on the left hand side. That input is going to go forward, right? And the first thing it comes across, if you take a look in this thing, here is our input, and it came across right as a straight path until it hit that amplifier that had a value B0. So I'm going to come in here and draw this guy in here. It comes forward until it hits that amplifier B0, which then is eventually going to feed into some summing nodes. And if I continue that going on, it's going to eventually come out to be my output y of t, something like that. What else does that x do? That x makes a beeline down, right? It comes down and it hits this other gain, B1, and it takes another path down and it comes in and hits B2. All of those guys go into summing nodes, and then there's an integrator chain in the middle. So let me go ahead and draw that out as well. So we said that we took that x of t, right, and we just let it go down, and that there was a point when it went forward and it went through that gain coefficient B1, and eventually a little bit later it came down here and it went through another coefficient B2, and that those all came into some summing nodes as well. So I'm going to come in here and come into some summing nodes. There's my summing node, and that there were some integrators in between here as well. So we had an integrator in here, and I'm including the arrows on all these lines here. If you go and check, all of these little arrows I'm doing in here are indeed the opposite direction from the original direct form 1 or direct form 2 structure that we were starting with. The last part on here are the feedback paths, right? So we have this value y, and it comes back around, and it comes back around, right, through two different coefficients, minus a1 and minus a2. So I should be able to get those in there as well. So I'm going to take this guy, bring it down, go ahead and have it bring it all the way down. And then there's that feedback, the first one, right? It's going to go through some minus a1, and then it's going to come into that first summing node there. And then this other one, right, has my minus a2 as being the last part of this structure. So this one is my transposed direct form 2. And some things that I might notice about this guy. The number of integrators, right, is equal to the order of the system. So this is also a canonical. It is a canonical system. So that's a happy face. That's a good characteristic. Canonical means that we're helping reduce the overall cost of implementation. The other thing that I would notice in here, right, is that here, this first part that x goes into are the zeros of the system. That's all the b's, right? That's from the p polynomial. And then it feeds into something that does all the poles of the system. So this guy has zeros, right? So it has these zeros and then the poles, right? And we said that that was also a good characteristic because it tended to help reduce the chance of overflow. So at least for the two kind of characteristics that I'm looking at, behavior of these circuits, this transposed direct form 2 seems pretty good. It's a happy structure, right? The only thing we really haven't done in this particular case is we haven't verified that the topology that I have here, that this transposed direct form 2 realization does indeed realize that original differential equation written as an integral equation. So let's go back up and grab that guy and we'll do a quick check of it. So we'll find that guy somewhere in here. And there it is. We've got that equation sitting in there. And I'm going to go ahead and make a copy of that. We'll bring it down and we'll do some checking on that as well if I can get it to copy. So, oops, that didn't work. Let's try it once more. So I'm going to grab this guy, copy it, and then we're going to bring it back down so that we can do some verification of the system's overall behavior. So go ahead and put this equation in here, and we'll do some comparisons. Let me try to clear out some of the other coloring so that we can do a clean look at everything. So there's the equation that we were trying, right, to realize. And we have a structure that we got by taking a direct form 2 structure, right, and then we transposed it using that 3-step transpose rule. There's other ways of also motivating that that we could look at during recitation if people are so interested, if they still don't like this. Okay, so let's go ahead and account for terms in here. I have x of t, right, and it's going to do what? It's going to feed through B0. So I get B0 times x of t coming and being part of my y of t. That's part of what gets summed in there. So there's my B0 x of t term, right? Then what else do I get? I get x times B1 integrated coming in. Well, that's B1 integral x. And I get x times B2 integrated twice, right, as being part of my y. So B2 double integral of x. And then I have y times minus a1 integrated coming in, right? That's that feedback one, so minus a integral y1. And then I have this other path that goes minus a2 double integral, something like that. That's this last one. So in this particular case, and you can't do this with all of these structures, some of them could get really tricky to do the following of signal paths and demonstrating it. at least from a time domain expression. Transform domain usually makes it easier, but this particular one we can easily verify that it does indeed implement the second order constant coefficient linear integral equation as expected. And it has the right characteristics. It's canonical, and it orders the zeros and the poles in the right kind of way. So we're just about done. The last thing that I would make a comment about is that we can do realizations for larger order systems in a variety of ways. So to wrap this thing up, oh, I didn't quite finish. Let's do one other one. We could, and I'm not going to derive this. I'm going to let you do it. So you derive, right? You derive to make sure that you can handle that transpose operation. You derive the transpose direct form 1. So start with direct form 1, apply the 3-step transpose operation, and get the structure. Okay, that's something that I'd like you to know. It won't be too much of a surprise here to know that this is going to be non-canonical. Okay, it started with a non-canonical structure. Direct form 1 is non-canonical. Its number of integrators exceeds the order of the system. Transpose doesn't change that, so it's non-canonical. That's bad. And it's going to reverse the order. If you remember direct form 1, it had zeros then poles. That was a good thing. If it reverses that, it's going to do poles and then zeros. That's also bad. So if you're just like a double pessimist and you'd rather do things the wrong way on everything, transpose direct form 1 is your structure. Almost no one would actually realize a system using transpose direct form 1. In theory, it is exactly the same integral equation. In practice, it's got some real problems. It's not terribly efficient, and it tends to have more susceptibility to things like overflow errors. Okay, the very last thing for our lecture today is going to be the following. If you remember our h of s, right? H of s is equal to some polynomial p of s over some other polynomial q of s. We can get that directly from our integral or differential equation, right? It is common to also write this in a slightly different notation. Sometimes people will call this guy b of s over a of s. And I think the only reason for that is if you look at this q in there, right, that guy's got a bunch of a's, right, and the p has got a bunch of b's. And so they're just letting the polynomial identifier here, b and a, help us remember that the coefficients are the b's and the a's from our original differential equation. So you can also do it that way. If I wrote this in a factored form, right, if I did b of s, it is an nth order polynomial. So I could do this as a product, and let's do it on k, going from 1 to n, right, of s minus whatever the zeros of the system are, right? This is just a factored form. And I can do that over a product, k equaling 1 to n, of s minus the poles, something like that. So we could draw this in a factored form as well. If I have that factored form, I can start doing all sorts of things. Like I can start grouping together terms in whatever ways I want to help in realizations. We've shown something right now that is a single stage representation of a second order system. We can, just by playing a few games with this factoring and how we group terms, do a variety of different implementations. It really can get quite interesting. So let me show by an example just one idea on here. So let's just assume as an example that I have an h of s, right, that looks something like this. Suppose it is an s minus j and an s plus j and an s, right? And I'm going to have, I'm going to just do it as a plus 2, something like that. And I'm going to have in the denominator for this one an s plus 1, and I'm going to have an s plus 1 plus j, and I'm going to have an s plus 1 minus j. So this is a third order system, right? This third order system in factored form, we can tell it's third order because you've got a cubic polynomial on the numerator and denominator both. We see that there's 3 zeros and there's 3 poles. It's also a real system, even though the zeros, there's a couple of zeros that are complex, one at j, one at minus j, and the poles also have a pair of complex poles. There's one at minus 1 minus j and one at minus 1 plus j. So if I did a pole zero plot of this guy, right, if I looked at where things were, I could look at that pole, right, as being minus 1 minus j, minus 1 plus j in there, and then there's just a minus 1. So I'd have something like that. There's those 3 in there. If I looked at the zeros of the system, there's 1 at j and minus j, and then I've got 1 at minus 2. So this is a little bit of a strange pole zero plot, but it is what it is. That's this particular guy. Because the complex roots come in conjugate pairs, if you multiply these polynomials out, you will see that when you multiply s minus j times s plus j, you will get a real set of coefficients. Let's go ahead and do that. So I'm going to get an s squared there, a minus js plus js. Those guys cancel. Minus j times j is a plus 1. So that's like an s squared plus 1, and I've got an s plus 2, something like that. If I do the s plus 1 plus j times the s plus 1 minus j, I'm going to get in the denominator, if I combine those two guys that are conjugate roots, I'm going to get an s squared, and then I have a 1 plus js, right, and a 1 minus js. That's going to be 2s, so I'll get a plus 2s. The minus and plus j's cancel, and then I'm going to get a 1 plus j times a 1 minus j, right? And if I look at those guys getting multiplied together, I'm going to get 1 plus 1 is 2, and so I will get a plus 2 in there. And then I also have my s plus 1. So this is also completely equivalent. So take a look at this, and maybe this explains a little better as to why we focused on a second order kind of stage. Here's a little second order stage, right? And all the coefficients are real because I combined, right, these conjugate roots together. And when you combine those conjugate roots together, the coefficients do indeed become real. So I could continue and I could multiply this guy out. So I could multiply this guy further out. I would get something like an s cubed, and I would have a plus 2s squared, right? And I'd have a plus s, and I'd have a plus 2. So I could do that in the numerator, and then I'd have to go through all this stuff in the denominator. I'd have an s cubed, right? I'd have a 2s squared plus s squared. That's going to be a 3s squared. And then I figure out where the s's are. There's a 2s plus another 2s is going to be plus 4s, and then I'm going to have a 2 plus 2. So I could also do it as that. I could just take this third order one and do a one stage, right? Something like a transposed direct form 2. That would be not a bad way to do that. I'd get a happy face, happy face. That would be one way of doing it. Here's another way of doing it, though. I could call this first guy H1, and I could have that being multiplied by H2. So I could call this guy H1, and this is H2. So I've got a product of two transfer functions giving me my transfer function, right? I could realize that system as a cascade, something like this, H1 and H2, to realize a single system. And this system would be like a second order system, and this is going to be a little first order system. And I could do these in whatever way I wanted. I could do this particular one, this first one, I could do this as a direct form 2, and I could follow that with a transposed direct form 2. Or I could have done the first one as a direct form 1, followed by a transposed direct form 1 if I wanted, or however you want to do it. We could interchange the order of this H1 and H2 in series. Depending on the poles and zeros and where they are, how we decide to group poles and zeros can be changed around. We can start playing with a lot of different ways of realizing these systems. We've shown structures here that are good for single stage realizations of these differential equations, but we can do series expansions just by grouping together different poles and zero combinations and making it as a product. We could also do this. We could take h of s, right? Do something like a partial fraction expansion on it. And what does that give me? That gives me something plus something plus something, right? And then we could do a parallel realization. We could do a parallel realization where we could do each one of these in whatever way we wanted. We could do this as a transposed direct form 1. I could do this one also as a transposed direct form 1. And I could do this guy as a direct form 2, or whatever it is that I wanted to. I'm not saying that people would normally have all these kind of variations in how they would do it, but there's lots of realization potential. When you get the homework, you'll see that a lot of them just involve doing a single stage realization, either using direct form 1, direct form 2, transposed direct 1, or transposed direct 2, okay? But that there will also be some problems that talk about series realization or this idea of a parallel realization, which will be based on factoring out the original transfer function or doing something like a PFA to make it into a sum of terms. That's enough for today. Next time we are going to talk op-amp realizations of these integral equations.